So I'm going to do one more example. I want you to do this example and tell me what is the unit step response of this system. So let us say I take this system for example, right? What are the values of n and m? N is 2, m is 1. The poles are still at -1 and -10. What about the 0? It is shifted to 2. So the 0 has gone to the right half complex plane. So if we plot this, the poles are at -1 and -10. The 0 is at 2 now. Okay, previously the 0 was at -2. What we have done is that we have taken it to 2. Okay, that's what we have done. Okay, please calculate the unit step response and let me know what happens. Is this correct? Right. So then what we are going to have is the following. Right, y of t is going to be -2. Of course, I have not simplified the terms, right? You can write -2/10 as -1/5 and 3/9 as 1/3 and so on, right? So yeah. Okay, so this is what you have, right? Am I correct? 12/90, right? So that's right. Yeah, sorry. Thank you. Okay. So once we have this expression, right? So for y of t, once again you could observe that the system is stable. Poles are in the left half complex, and poles are the same, right? I've kept the poles to be the same in all these problems. Why? Because we want to investigate the effect of zeros. So I'm not even touching the poles, right? So we are working the same poles, right? So we have shifted the 0 to +2 to the right of plane. So the system is still Bibo stable. What can you say about the steady state value as t tends to infinity? The value of y of t goes to -2/10, right? So the value can be negative also, absolutely no problem. It needs to be a finite, real number. That's what we want, right? And you can once again observe that the exponential terms have the poles as the exponents, and the residues are also affected by the location of the zeros. Now we see that compared to example 2, the relative importance of e power minus t has now increased because we have shifted the 0 away from -1. See, -1 was the dominant pole. When we had the 0 at -2, the dominance was reduced. Now we have shifted the pole to away from the dominant pole at -1. You can see that the relative magnitude has once again increased. The dominance has once again increased. That means that the magnitude of the e power minus t term is 3/9 e power minus t. This is 12/9 t e power minus 10 t. So you could immediately observe that the 3/9 e power minus t term will dominate. Okay, fine. So that is the first observation. Okay. So any other observation here that you can make?
I'd like to ask, does the closest to the other pole matter? closeness to the other pole.
It matters, right? So if you move the 0 closer to -10, that dominance, the effect of that pole will go down drastically, right? So even without a 0 near to it, like it's anyway its effect is small. So
regardless of the pole being dominant,
so the 0 will decrease the residue, but we are practically, from a pragmatic viewpoint, we are interested in what is happening at the in the vicinity of the j omega axis, right, due to this point, right, because the poles located in the vicinity of the j omega axis would dominate the dynamics. Okay, so that's why they are called dominant poles. Okay, yeah. Okay, so can you observe something else? No. So suppose if I want to plot y of t versus t, sorry. For this, what is y of 0? Of course, I can always double check. See, whenever we are using this analysis, we are assuming initial condition to be 0. So once you complete the problem using this transfer function based approach, it's always a good idea to substitute t equals 0 and ensure that y of 0 is 0, right? Because that's an implicit assumption that we have made. So you see that I start from y of 0 is 0, right? And let's say this is my final value. Okay, so this I leave it to you. You can go to MATLAB and plot this function. Let's say this is -2/10. So what's going to happen is that the output function will go something like this and settle down to -2/10. Okay, that's going to be the impact of the 0 at 2. Yes.
Because we change the 0, as you change the 0 towards the right, it become more and more negative.
Which one?
The final value of
yeah, it depends on how you write it. If I write it as 2 minus it, it will become positive. See, the sign can be negative or positive. Okay, you are right. If I go further to the right, okay, it's going to become one sign or the other, okay, depending on how I write it. See, for example, if I had given you the transfer function as 2 minus s divided by s plus 10, s plus 1 times s plus 10, till you will have a 0 at 2, but the final value would have become 2/10, right? So it really depends, okay? Yes. So, but the important effect is this, right? So in all the previous problems, once again, please go back and plot the output functions, okay? What do I mean by output functions? These boxes, the blue boxes, the green boxes, whatever y of t I have enclosed in those blue and green boxes, right? So you will see that in all those cases, the initial value is 0, and you will see that the output would monotonically increase to the change to the final value. What do I mean by that? It is not going to change signs, okay? So for example, the final value is 1/10 and 1/5. The output function will always be non-negative. Okay, it will go from 0 to the final value smoothly, right? So without changing its sign. But in this particular problem, if you plot the output function, which is enclosed in this red box, you will see that it will be at 0. It will start at 0 at time t equals 0. Final value is going to be negative in this particular example. Okay, it will so happen that initially it will go, the values will be positive, then it will change sign, and then it will come to the final value at -10, 2/10. If I return 2 minus s, it will become negative and then it will go to positive 2/10. Okay, the effect is going to be reversed. Either way, like the conclusion that we can draw is that if you have a 0 in the right of plane, your step response is going to have such a characteristic where the response will start off in one direction, then reverse its direction and go and settle down in that way. So let me give you an example. Let's say we take a ceiling fan, right? Suppose if the ceiling fan had a 0 in the right of plane, right? What will happen? Let's say I switch on that fan. What will happen? It may start rotating in, let's say, clockwise direction. After some time, it may stop and then start rotating in the counterclockwise direction. Picturize that, okay? That's this case. Suppose if I had a door which was a non-minimum, which has a 0 in the right of plane, what will happen is that, let's say if I push the door, I expect it to go out. Imagine a door if it comes in and then goes out, right? So that. Fortunately, doors are not like that, but then you can imagine it, right? So that's going to be the effect of this 0 in the right of plane. And zeros in the right of plane are called as non-minimum phase zeros. Okay, we will figure out why it's called non-minimum phase when we do frequency response. Okay, we will see what is the meaning of the adjective non-minimum phase. Okay, when we come to frequency response. Okay, but those are called non-minimum phase zeros. Okay, so what is the definition of non-minimum phase zeros? Zeros in the right of complex plane, complex plane, right? And a non-minimum phase system is one which has zeros in the right of plane. Okay, and a minimum phase system is one which has all poles and zeros in the left of complex plane. Okay, so that is the definition of minimum phase and non-minimum phase. Is it clear? Okay, why it's called non-minimum phase? In what way is the phase non-minimum? We would see first of all what is phase as per our definition is concerned, and then what is minimum non-minimum about it. We'll look at it when we come to frequency response. Okay, so that's something we'll learn later, right? But that's the impact of non-minimum phase zero. Yes.
Also, the final value of y of t seems to be the constant in the numerator divided by the.
Okay, good observation. Okay, so you can always see that in all the examples. Okay, you have essentially preempted my discussion on steady state analysis. Okay, that's good. Okay, I'm happy that you have made that observation. What his observation was that not only this problem. You take problem 1, you substitute s equals 0 in the transfer function. What do you get? 1 by 10. Second problem, substitute s equals 0, 2 by 10. And what are 1 by 10, 2 by 10, minus 2 by 10 in these three problems? It is the steady state output of a stable system when subjected to unit step input. Okay, but then we will generalize it. Okay, please do not substitute. Okay, that's why I'm telling you this because he made that observation. Okay, but I wanted to teach it in a different way using the final value theorem. See, we learn the final value theorem, right? You'd use that. Okay, so kindly, keep this in mind, but do not always substitute s equals 0 to find the steady state value for any input. It doesn't work that way. Okay. It only works for this unit step input and that too for stable systems. Okay, so please remember that, right? Okay, so anyway, we will come to that. That's a good observation, but we will come to that. Okay, now the question is, when do we get a non-minimum phase system in practice? Okay, like so, I have to give you an example, right? So when can we get see, if you leave the system design to me, I would obviously never put a 0 on the right of plane, right, due to this limitation. But can I get a 0 in the right of plane by the system's characteristics itself which is given to me? Yes, I can. Okay, because I can get non-minimum phase zeros, right? For example, when we have an example of a non-minimum phase system, okay, when we have a system with time delay. Okay, so let me take a simple example. Let's say I take y dot plus y of t is u of t minus td. Okay, td is the time delay. So that what it means is that I give an input now that's going to affect the output only after an time interval of td. Okay, that's the time delay, right? So can we encounter time delay in practice? Yes, we do, right? Suppose, let's say, I want to push this desk. The force which I am applying is my input. And the displacement of the desk is the output. Will the desk start moving instantaneously? Does it? No, right? Why not? Exactly, right? You have to overcome static friction at the point, the region of contact between the desk legs and the surface. Right? So even if you start counting time from the moment I start applying a force on the desk, right, the displacement happens only some time afterwards, right? So that's a delay, isn't it? Okay, so friction, for example, right, incorporates a delay in a system. Okay, so we'll see that many cases, like you may have delays. See, for example, like let's say I may give an voltage input to a motor. The motor shaft may not start spinning immediately. right? It may take a small interval of time before it starts spinning, right? So question is that, like, is the delay time significantly high when you compare it to the time scale of interest? Okay, that's a question we need to ask. But assuming that is the case, then what do we do, right? So I have to factorize time delay. Let's say now I want to find the transfer function, right? You take Laplace transform on both sides. What will happen? What would happen if you take Laplace transform on both sides? What will you get? You will get s times y of s minus y0 plus y of s. What is the Laplace transform of u of t minus td? U of s times e power minus tds. Okay. So now take initial condition to be 0, then the Planck transfer function, which is y of s divided by u of s, is going to become e power minus tds divided by s plus 1. Right? Now what are the values of n and m? What is the value of n? 1. M? 0. I have e power minus tds, right? How can I expand e power minus tds as a polynomial expansion? Yes. What will be the order of that polynomial? Infinite, right? So I can just go to any order I want, right? So I have a problem now. Okay, because the system has become infinite dimensional in a sense, right? The Planck transfer function, right? Because you see that the numerator has e power minus tds, which I can expand as a series expansion to an infinite order, right? So we have a problem now, correct? So because we can apply the tools that we are going to learn in this course only for proper transfer functions. That means that we need to have the order of the numerator polynomial to be less than or equal to the order of the denominator polynomial. Okay, that's when we can apply the tools that we are going to learn in this particular course. Okay, so given this limitation, like what is it that we can do, right? So we can do approximations, okay, of time delay. Fine. So provided like TD is small, okay, TD is sufficiently small, okay, like I am going to write all these things in quotes, okay. Okay, so how do we do this? Like one approximation is that people will just write e power minus tds as what? 1 by tds plus 1, right? Correct? You can write e power minus tds as 1 divided by e power tds. You just take the first order expansion of e power tds and stop there. Okay, that's an approximation, right? So a second approximation is saying, look, I will write e power minus tds as e power minus tds by 2 divided by e power tds by 2. Okay, so I am splitting the exponent by 2. So I am reducing it even further in a certain sense, right? So then what I do is that I use a first order approximation for both the numerator and the denominator. So I get 1 minus tds by 2 divided by 1 plus tds by 2. This becomes 2 minus tds divided by 2 plus tds. Okay? So this is what is called Paday's first order approximation. Okay. Of course, if you use the above approximation, the Planck transfer function approximately becomes 1 divided by s plus 1 times tds plus 1, right? So this becomes like a second order system, an approximately second order system, right? So that's why what happens is the first approximation. So now if I use a second approximation, what happens to the Planck transfer function? It approximately becomes 2 minus tds times S plus 1 times 2 plus TDS. Okay. Now, what has happened? We have introduced a non-minimum phase 0, right, through this approximation. You look at the numerator, right? TD is anyway positive. What is the 0 of the transfer function, approximate transfer function? 2 by TD, right? So, that is going to be in the right of plane. Okay. So, due to that, what will happen is that if you if you plot the step response, what is going to happen is that, so the output will go like this, and then like it will go on, oops, it may go like this and then go and settle down, assuming that we are stabilizing the system carefully, right. So, this is indicator of the time delay. In reality, what is going to happen is that the real system output may be something like this. Okay. So, let me show it in blue. Okay. So, the real system, let us say there may be a time delay, and then like it may go and go like this. Okay. So, in this interval there is no output at all, but then the approximation essentially tells us that, oh okay, the output may go in the opposite direction and go in the correct way. Okay. So, the pink curve is only an approximation of reality. Okay. And why are we doing this approximation? Then only we can design, right. See, I cannot design with this guy. Okay. The tools that we are going to use in this, learn in this course cannot be used for this transfer function, but I can use it for this transfer function. Okay. So, that is why we approximate, but the impact is that we introduce a non-minimum phase 0, which is going to behave like this. Okay. The dip in this curve is a fictitious dip. It does not happen in practice, right, because during that period the actual output is going to remain 0 due to time delay. So, what it says is that, okay, look, if I model time delay for this disk, okay, the actual system response will be that if I give a step force, it is going to remain 0 for some time, and then like it is going to move, right. So, that is what is going to happen. But what I am predicting through this approximation is that if I apply a step force, the disk is going to come slightly towards me and then go backwards. In reality, it is not going to happen, but that is the approximation we are going to have. Okay. And why are we doing it? Because the tools that we learn can be used only when the transfer function is proper. So, we are using this approximate transfer function. Okay. So, I hope it is clear when we can encounter non-minimum phase zeros, right. When we have to incorporate time delays and do the design process, we have to do this, right. We introduce a non-minimum phase 0. Okay. So, what we have done in today's class is essentially look at the influence of zeros, right. That is what we have done today. So, we have looked at impact of poles yesterday. So, starting from tomorrow's class, we are going to look at, as I told you, stability and performance, right. We have looked at stability, and tomorrow's class onwards we look at performance specifications. That will complete the system block.